Okay, continuing with functions, let's consider a function y equals f of x. And by the way, if we had something like f of x equals 2x plus 1, well, the f of x, sometimes I will write this like y equals, and here's f of x, the function of x, 2x plus 1. But when you have something like this, the two variables, x and y, have particular names. If we have y equals f of x, something like this, x is the independent variable. And then you can probably guess that y is going to be the dependent variable. I usually think about that as I'm making ordered pairs if I'm going to graph a function. Well, I plug in values of x to find out what I get for y. The value of y depends upon the value that I choose for x. Okay, going back to review a little bit. This is a picture where we have a set A and a set B. I've shown two specific elements in A. And what this graph represents, this picture represents, is that f of x1 is equal to y1. It also says that f of x2 is equal to y1. So the question is that a function? And based upon what we see here, sure, that's a function. You're allowed to have two different values mapped to the same number. You are not allowed to have one number mapped to two different values. Well, actually, that's the next example. I'll try not to refer to this as function. I'll call it maybe a relation, not a function. G. G is, this is a function. This one is not a function. Because notice that if it were a function, I would say g of x1 equals y1. But also g of x1 equals y2. That means it's not a function. So pictorially, if you ever have a point, an element of A that has two arrows coming out of it, meaning it's getting mapped to two different numbers or more, then it's not a function. The last one is a function, but I just wanted to demonstrate that the image of the function h does not have to be the whole codomain B. This would be h mapping A into B, but if you take h of A with all of the values of capital A in here, it might only get mapped to a small number of values inside of B. So this part here that I've shaded a little bit, that would be called the image of the function h. B is the codomain. H is the numbers that actually get mapped to. H of A is, that would be the image of the function h. Okay, I think I'm going to need a little bit of room, so I'm going to erase. We have 4 examples, and we need to determine which of the 4, if any, is a function. And if it is a function, find the domain and the range, if it's a function. So, the first one. F, we're writing it in this form, the ordered pair form. It's all of the ordered pairs x, y, where x can be any real number, and y then depends on x, is x squared plus 1. So for example, if x is a 0, then y would be 1. Is that a function? Well, I'm going to look at it 2 ways. Is there any number I could plug in for x, any number, that would give 2 values when I square it and add 1? And of course not. If I take the number 5 and square it, I get 25. Add 1, I get 26. When I plug in a 5, I get only one number. Therefore, this is a function. And another way to look at it is if you graphed that, that'd be 1. It would look like this parabola. And I'll mention this later, but any number that you pick on the real line for x, f of x has exactly one value or one height, maybe whatever that is. So clearly number 1 is a function. Number 2. Oh, sorry about that. Let's go back to number 1 and do the domain and range. Well, the domain really is specified here. It's defined for all the x's in the real line. So the domain is all real numbers. So, what are all of the possible y values when I plug in all the possible x values? It's really easy to see when you look at the graph. All of the possible heights are taken. Note the function can never have a height of 0. Never has a negative height. The lowest possible height or value of the function is 1, but it takes on all of the other heights up to infinity. So the range is the interval from 1 to infinity, with the interval being closed on the left-hand side because 1, if you plug in a 0, you get a value of 1. Another way of looking at it is, if you're squaring a number, the smallest it could be is 0. Because if you go plug in a negative, it's going to become positive. A positive is going to remain positive. So, this x squared can be any number from 0 to infinity, but we're adding 1 to it. So the smallest this can be is 0 plus 1, which is 1. Okay, that takes care of number 1. Number 2, set of ordered pairs where x is in the set of real numbers. It looks similar to this, so you might be tempted to say, of course, it's a function. But of course, it's not a function. And we don't have to graph it. We just need to use the definition. What does it mean to be a function? It means that each value of the input for each first variable x, there's only one y that corresponds to it. Well, let's consider x equal plus or minus 2. Two different values. Sorry. Y equals plus or minus. I can pick any integer to make it nice and easy. Okay, let's take y being a 2. If y is a 2, it would be the ordered pair 2 squared plus 1 for x, 5 comma 2. Or, if y is a negative 2, we get negative 2 squared, which is 4, plus 1, which is 5. We just proved, using a counter example, that this is not a function. We found two ordered pairs on this function where you have the same first element, the same x, getting mapped to two different values of y. I could have picked plus or minus 1, plus or minus 3, plus or minus 4, plus or minus any number, and we would have found this contradiction. So this is, I'm not going to put a check mark by it, I'm going to put an X. It is not a function. The next one is a little tricky. We want all the ordered pairs where the first number comes from the real numbers, and y, the second value, is 1 over that number. Well, you might be tempted to say that it is a function, but because we're defining it for all of the values of x in the real line, and that means x could be 0, it means this is not defined for 0. So this is a tricky one, but no, not a function, because f of 0 does not exist. 0 does not have an image. And if I could make a small change to this and make it a function by saying x, instead of x in all the real numbers, I'd say all the real numbers except for 0. Then this would be a function. All right, the last one. This one will take a little practice too, or a little thought. It's a set of ordered pairs, this comma this, where the first one is x over y, so y better not be a 0. And the second term is x plus y. Now let's see what this says. Such that we're only dealing with integers. X and y are integers, and y can't be 0. Okay, so we're not going to get a division by 0 at all. That's great. So what do you do when you don't know the answer immediately? Remember what we do? You try things. And after you try some things, you may find a pattern and say, oh yeah, I can see that this is always going to be true. Or you may try something and say, oh, it failed right there. So I know it's not a function. Well, in this case, let's take a fraction like 1 over 2. Let's say x equals 1, y equals 2. All right, well, those are perfectly valid numbers to use. That means we get the ordered pair 1 over 2, comma, 1 plus 2. Okay, well, you can't find a contradiction with only one point. Let's plug some others in. And notice that there are an infinite number of fractions that are equal to 1/2 when you are using the integers x and y. Let's now go over to x equals 2, y equals 4. That's going to give me an ordered pair, 2 over 4, comma 2 plus 4, which is 6, which is equal to 1/2, comma 6. Hopefully you can see that. So this, if it were a function, this case wouldn't happen. We found two ordered pairs represented here, 1/2, comma 3, and 1/2, comma 6. Those are contradictory of being a function because the first value, the x value of 1/2, gives two values when you take f of that. And actually, we could find an infinite number. If we just chose x equals 3 and y equals 6, or x equals 5 and y equals 10, we'd find out that there's an infinite number of second values corresponding to 1/2. 1/2, 2/4, 3/6, 5/10, and so on. So that was a little tougher, but you just had to try some examples to convince yourself that this is not a function. So I will put an x by that one as well. So in our three examples, only the first one was a function.